trying to be robust is to limit the complexity of the policy. Try to have as few parameters in the policy as possible, and somehow it seems that that generates more robust controllers. This says never do deep reinforcement learning. What I'm going to advocate is what we should be doing is design policies for multiple models. If you design for a set of models, then hopefully you will be robust across that set. An implication of this is we have to use policy optimization, no more dynamic programming, and no more trajectory optimization. Because what we're optimizing are parametric policies. And the way you do that is incredibly simple. If you had a single model and you wanted to try out a policy, you'd run it for a certain amount of time. Maybe you'd pick a set of initial conditions and run them from all the initial conditions and average or add up all the costs. And all I'm saying is, in addition to doing that, you should sum over a set of models. Now, this is a weight that depends on how much you care about the model and the starting point, and this is a notation of the cost given a particular model with that starting point and this vector of parameters. And as long as there's a finite weight on all the models, you're pretty, yes, you can get into a fixed amplitude oscillation or something like that, but none of the models are going to blow up to infinity.
So can I ask you, now you made a big change. We went from trajectory optimization, right? First,
yeah.
Our initial and final state that we're trying to
Correct.
To having a general policy. I want to still have a question regarding the trajectory optimization part. Do you think that if we just learn local linear models of the environment, okay, we initialize them with local linear models, and then we try to use the learn model instead of the model, the structure model we imposed, which may be wrong? Do you see what I mean?
That was, you remember me swinging that thing up? That's what we were doing, is learning local linear models throughout the space and then doing trajectory optimization through it. And clearly that works. It has a couple bugs. You can get into a situation where your action generates new knowledge that does not change any of the models you were actually using. So you keep saying do the same thing over and over again. And so you get stuck. A way to fix that is to add in a little bit of model-free learning where you basically use the error to directly drive or explore to generate a new command. And that usually gets rid of the problem of getting stuck. So mostly model-based learning with a touch of model-free learning is a good combination. Okay, so we're interested in doing this model-based policy optimization with sets of models. We can compute numerically a first-order gradient and a second-order gradient, or we could use a non-gradient optimization algorithm such as something called CMAES, which is very popular. The only change we do with multiple models is we add an additional sum over the multiple models. The gradient's just sum. And in the example I gave you, the system trained on multiple models, and the nominal expectation was you would have done that. When you're actually given the real system and the actuator has limited bandwidth, you do something very reasonable. You're a little oscillatory, but you're not blowing up to infinity. Now, you might say, for n models, I have slowed down my learning process by a factor of n, which is not that bad. But if you're willing to use a model-based trajectory optimizer called differential dynamic programming, which is the granddaddy of ILQR and a lot of other algorithms, which are basically reinventions of differential dynamic programming, you can analytically propagate gradients very efficiently with local linear models. And you can handle constraints. I'll put these slides on the web. I'm going to flip through these very quickly. You can actually compute second order derivatives or Hessians in order to do second order optimization. You can regularize these things. When you know your model's bad, you can actually add additional quantities to the second order optimization process so that you're conservative when your model is bad, which is a good thing to do. All right, I'm going to skip some examples. There was a quick example where we had a linear, quadratic, bilinear regulator. I'm just going to skip that. Okay, so here is our manifesto about making robust policies. We think training on multiple models is a good way to go. I highly recommend it. A lot of alternatives, like finding ways to invert or cancel the nonlinear dynamics of a nonlinear system, are simply bad ideas. You need to choose the set of models you're going to optimize over very carefully. We also believe in massive amounts of redundant sensing are very good for reliability, and self-monitoring is also very good for reliability. We were the only team in the DARPA Robotics Challenge that did not fall down and did not need to be rescued by humans, and tried all the tasks. And the only reason we did not fall down was we had a separate process that was looking for screw-ups. And when it detected a screw-up, it froze the robot, and the robot asked for help from the remote operator, which was allowed. So for example, the robot's trying to go through the door. Most of the time we went through okay, but one time the protective cage around the head hung up on the door frame. We detected that. So when that happened, we're always estimating an external force on the robot. That should be close to zero because we don't believe anyone's pushing on the robot. And when it suddenly changes, freeze the robot. Another thing we did, we were trying to drill a hole in the wall. Our wrist broke. The robot started pushing too hard. This is what's called the center of pressure. This is the polygon of support. Going outside the green area is bad. We detected that the center of pressure was going outside the green area. We froze. While the humans were scratching their head, the robot's sort of on the edge, sort of wobbling like this. And then the human said, okay, here's what to do, and we got it balanced again. And the wiggly lines looked like this, and basically we expected that increase, but we didn't expect those spikes, and we froze the robot. Here's another example. The robot's walking across a bunch of cinder blocks, and it places its foot so the toe's on one set of cinder blocks and the heel is on another set of cinder blocks that are at a different height. So the foot's like this. That's really bad. Again, we detected, wow, this is not what we expected. Freeze the robot, ask for help. So don't just think about how to design a controller. Also think about how to monitor yourself for errors. Okay, now in the final section of the talk, I want to talk about what I think is the most important learning problem. And I feel it's pretty much totally ignored. And it boils down to finding better ways to do behaviors that are somehow easier. When I was in high school, my math teacher said that I would go far in life because I was so incredibly lazy. And I spent a lot of time thinking about how to minimize the amount of work I had to do. We need lazy robots. We need robots that cheat and find easier ways to do tasks. And let me show you some examples. This is a picture of our robot from the DARPA Robotics Challenge. We successfully walked up these stairs. This is the end of the run. We're totally happy. What is wrong with this picture? Even drunk people know to use the railing. Okay? Now, it's not that I like to dump on MIT. The MIT team put out this video showing their robot stepping out of the car onto the platform and eventually here. I don't know how long you want to watch this. It's a little weird, kinky. The graduate students are jumping up and down on the vehicle's shaking, and the robot is very slowly standing up, and eventually you get her feet here, and eventually step down here. This is an incredibly impressive demonstration of robot control. The thing can stand up and even move when the floor underneath it is shaking. It's amazing. These guys probably spent a year working on it. What is wrong with this picture?
Can hold the black.
There's a handle. They put a handle right there. It would have been so much easier if the robot just grabbed the handle. You don't have to have a $2 million robot. You don't have to have graduate students jumping up and down of the car. You don't have to have exquisite control. Just grab the handle. Okay. A shocking fact is that no robot grabbed railings, walls, door frames, or anything else in the DARPA Robotics Challenge. A few robots, ours included, did touch things in order to get out of the car. We flung ourselves onto the hood of the car. But it's shocking that all these people work so hard to do things the hard way. And if robots could look at a problem and say, oh, the easy way to do this is such and such, robots would be as good as humans. Current robots would be just fine. Our problem is robots don't have a clue as to how to find the easy way to do something. Now, because I think this is the most important problem, and I think all of you as graduate students should be working on it and drop whatever else you're doing, this is really the most important thing. I did some investigation about how people learn strategies. Here is an example of a program for people that explains to them how to do the Macarena. It's pretty straightforward, it's very qualitative. I looked at juggling how-to books. These are particularly interesting illustrations because they're physically impossible. No matter how you throw the ball, it's not going to do a 90-degree turn in the air by itself unless it has rocket engines. Similarly, it's not going to do a curved line unless it has rocket engines. Yet somehow, this is very useful information for humans and programming humans. Now, this may not make sense to people not from the United States. We used to have a television show called MacGyver. Recently, they revived it, so I believe it's still on. And MacGyver was famous for improvising ways to do tasks. And what we need to do is get a MacGyver robot. And if you do anything with deep reinforcement learning, figure out how to do this. And there's just all these tricks, binder clips to hold your cords. If your screw is stripped so your screwdriver can't turn it, put a rubber band between your screwdriver and the screw. Works like a charm. Look at this trick so you can drill holes into your neighbor's cubicle and you collect the dust. That's amazing. Have you ever had the problem of putting too much pancake mix in the pan and the pancakes are too big? Put the pancake mix in a squeeze bottle and you have total control. Okay, if you're not impressed by that, here are the things MacGyver did in the original show in the pilot. He disarmed a missile with a paperclip. He used matches and rope to set up a way for a rifle to shoot by itself. He smashed a pistol barrel to use as a rocket thruster. He kicked a grate to test for hidden layers. He lit a cigarette using smoke to look for hidden lasers. He smoked a cigarette to find the hidden lasers. He used a binocular eyepiece to catch a laser beam and aimed it at somewhere else to kill something. He knotted a fire hose to build up water pressure and used that hose as a jack to lift the steel beam. Amazing. He tested the heat on the door not by touching it with his fingers, but by touching it with a stick. Since the stick started to burn immediately, that door was very hot. It turns out milk chocolate candy stops the sulfuric acid leak. Who knew that? He used his shirt to filter gases he created an explosive out of sodium and a cold pill, and he flipped lights in Morse code. And in fact, really anal retentive people have collected all the things he did in all the shows if you want to take a look. Okay, so I want to explore this issue right here and now. The very tough issue we're going to talk about is how to open a jar that is stuck. Now, if you're in robotics, you'd say, well, you could use a power grip to open the jar. Or you could use a precision grip to open a jar. And that's about as good as robot planning gets. Let's talk about human planning. I want to ask you how you open jars that are stuck. So, anyone want to volunteer how you open a stuck jar? How do you open a stuck jar?
Bang on the lid.
Okay, bang on the lid. So my list of questions are, did you invent that strategy? Where did it come from?
Where did I get it from?
Yeah.
My mother.
Excellent. All right, why does it work?
So my theory is your theory is that oh no, that is your theory.
I'm the break the seal school of thought.
Okay, yeah, my theory was that it breaks the friction seal, not so much the pressure seal.
Okay, how do you open a jar that's stuck?
More power.
Well, you just try harder. Or you get some friend who's really strong.
Yeah.
How do you open a jar?
I think maybe more power. With my close to interpretation.
More power, wow. How do you open a jar?
With more air coming.
So you just find a way to pry it and break the vacuum. That's excellent. How do you open a jar?
I asked somebody.
You ask somebody else. That is a version of the more power strategy. How do you open a jar? Okay, so that's the tapping strategy. Does anyone have a non-tapping strategy? Run hot water on it. Why does that work? Okay, so that theory is you're relieving the vacuum. The other theory is the metal expands. Which theory do you believe in? Does it matter whether your theory is correct? Wow. That's really sad. Did you make up that strategy yourself? Okay. This is really shocking. What's that? Yeah, use a knife to pry it open. This is really, really shocking. We've established two things through my statistically valid survey, which is, one, humans don't invent new strategies. They learn from demonstration or imitation. So forget reinforcement learning. And the second thing is, it doesn't make any difference whether the theory which guides their behavior is correct or not, as long as the behavior works. So that suggests learning policies is a good thing, and adapting policies so that perfecting them is a good thing. So maybe reinforcement learning is not as bad as I thought. Anyway, I did a survey on the web. Here are pictures of various ways. One of the things we didn't mention is you can use some soft material between you and the top of the jar, such as rubber bands. They sell, or a tennis ball, but they sell these special surfaces. You can whack it. You can whack it with a spoon. You can pry it with a spoon and knife. You can whack on it with a can opener. Pour hot water. Put it in hot water. This is weird. Use duct tape. You can put a nail into it to relieve the vacuum, and you can ask someone who's stronger. Here's some more pictures. You can use a blow dryer, rubber bands, sponge, pry, gloves, a lighter. Okay. What is this? You clap your hands? Throw it at the wall. So nobody said break the jar open. There are even tools that are invented for this purpose. Okay? You can buy them. The name of this tool is a Gilhui. Okay. You can even get power tools to do this. You know, this is from a late night infomercial. And you know, you can screw something to your cabinets to make this easy. What's it going to take to get a robot to learn from the web and all this material? I think that's a really important question. A second question is, what's it going to take for a robot to invent these kinds of strategies rather than just learn them from imitation? A third question is, maybe that's the wrong question. If humans don't invent these things, they learn them from other people, and you know, we have to wait until we have an Einstein to invent a new way to open a jar, and they're very rare. If you look at the records in sports, you will see sports records such as high jumping improve very slowly for 10 years and then jump up when Einstein comes along and says, here's a new way to get over the bar, and then another 10 years and another Einstein comes along. People who invent new strategies are actually, I think, very rare. So maybe that's the wrong thing to ask your robot to do. I would very much like to have a robot that could reason about physics and explain. It doesn't have to invent the strategy, but it has to make up an explanation, even if it's wrong, of why the strategy works. Now, I'm going to get fired for saying this, but I'm going to say it anyway. I'm sorry, I can't do it. What I just said, did you hear what I just said? I want a robot to make up explanations of why things work. Can anyone suggest an English word that describes what the robot is doing?
Being president of the United States.
Okay, that's good, but not what I was looking for. Okay, anybody else? I want a robot that mansplains. Okay, wasn't funny, sorry. I thought I'd insert an advertisement on this tactile sensing thing with cameras. So the tactile sensing thing with cameras allows you to, for example, very gently pick up an origami bird without crushing it. Why? Because you can actually detect slip. You can't measure the forces, they're way too small. And when somebody grabs the bird and starts pulling on it, the robot can let go. Now there's a much longer video on YouTube. Here I'm showing you, yes, we can see the finger, and then when we press on it, you can measure displacement of markers, and that gives you forces.
You said you can pick it up because you can figure out when you're picking it up, right?
That it's not slipping. You can close enough so it's not slipping, and if it starts to slip, you close more. That's a very simple algorithm. Okay, so that was my advertisement. Now we're going to return to our regularly scheduled program. Yeah. Say it again, please.
Is that the transparent skin you were talking about?
Yes, yes, so you can see through it.
I see. So you use the dots essentially as a way to...
We add the dots so we have something to track on the skin. So you can see the cocan through the skin, and we're using vision to look for optical flow. Okay. There's a guy, Mark Rabert, and I wanted to tell his story. He was about 10 years ahead of me in the MIT psychology department where we got our PhDs. And he did his thesis on learning. 1978 is the article. And this is the robot he did. And he basically did the arm farm thing with one robot. He wasn't picking stuff up. Instead, he was figuring out how much the robot weighed, what are the inertial forces, all that kind of stuff. So it was kind of funny to me to see this, and then 40 years later, see roughly the same thing. Rabert, on completing his PhD thesis, swore that he would never again have a robot learn. And so far, he's kept that to be true. Yeah?
You got to tell him his right hand frame is wrong.
I could have screwed up the photo. This is actually what's called a Vic arm from Victor Scheinman. So maybe Victor just defined the coordinate systems badly. But yes, that is a left-handed coordinate system. Okay, let me talk about one of the big successes in deep learning, which is this learning the graph speed stuff, and raise a couple of issues there. I hope Laryl isn't here. Okay, here and at other places, we've put out stuff on a table, and eventually a robot learns to pick it up. And you know, the argument is we can do big data approaches because amazingly enough, the Baxter robot runs for a long time without maintenance. That blows my mind. I bet we could do these experiments in simulation and do just as well. So you can either think of that as big simulation or big fake data. I can tell you that the community of people who works with high performance robots looks at this work and says, why are we investing all this research effort on essentially very crappy hands and very crappy robots? Wouldn't it be better to use higher performance robots and higher performance hands? Okay, I wanted to end there because I hope to provoke some discussion. Any thoughts? Yeah?
In the same way you can learn on a crappy robot, you can learn on a high-performance robot without needing more students, just letting the robot figuring it out. Apart from that, it's fantastic. Like you were saying, inventing new strategies. I mean, people that are not healthy and they have very few fingers, somehow they manage to manipulate a lot of things with different ways than
Yes.
the rest of us.
Yes.
So our robots should also be able to.
Yes.
So the proof of concept is there that you can.
Why don't you make that an assignment for the class? So it'll be solved. Other questions? Thoughts? Yeah.
My robot's not even close to like learning brand new strategies yet. I want the robot to do something, and I want it to learn. But I don't want to. It doesn't need to do everything, and I need to be able to help it. So how can I occasionally inject help in that?
I think the one biggest thing we can do to get more useful robots is make learning from demonstration work. Because it's so much easier to teach in that way by demonstration than to program.
Yeah, programming anything takes a really long time.
Right.
So how do I do that?
Well, we're cranking away. The field has a pretty good answer to how to do learning from demonstration if the teacher has the same shape and kinematics as the learner. When we start having teachers that are human and have robots that have multiple arms, more than 2, for example, and have cameras all over their body so that they have different capabilities than a human, then we have to figure out how to abstract what the teacher did. And I believe we need cognition, thinking, in order to do that, thinking about physics. And then you have to transfer the thinking and re-implement it on whatever the robot is. And we don't know how to do that.
So, I mean, like in the DARPA example, there's an abstraction built in with the hierarchy.
Right, generated by humans.
Yeah, and ideally, I'd like to do something. I'm willing to invest some effort, but I don't want to invest 10 years in developing a hierarchy for a specific robot, specific task.
You're not willing to sacrifice your life to robotics? Why are you here?
I want to accomplish. I want to accomplish something more general. Right? How do I do that?
If I knew, I'd be selling it to you. So I don't know is the answer. Yeah?
Here's my question. It seems that roboticists care and are impressed if a robot does in a very controlled environment a very complicated thing. You want to show to people and say, wow, that requires skill. Like it seems like
Yes.
While the robot seems it cannot even go into the door without figuring out that it crashed on the door, and then you need to, the teleoperator needs to tell them, oh, freeze, I'm going to control you now. I think this is against the philosophy of learning, that first we need to learn simple things and then we need to learn complicated things. If we go straight for the complicated thing, even if you learn it, even if you get impressed people, you cannot build on it. You don't know how to compose, you don't know how to go from there. But you learn how to do this, and then what are you going to do with it? It ends there, and then you start a new project.
So you've articulated what I would call the developmental point of view, where we should develop robotics and AI by essentially imitating the developmental process of children, going from being a baby to 20 years later being a sullen teenager. It is true that's a very attractive paradigm. A lot of people have tried to do it and not gotten very far. My personal bet is that that's not the right way to go. It's an interesting way to go, but my personal goal is sort of adult level competence, and I think the best way to get there is by directly attacking adult level competence. I agree with you, we are to some extent missing the boat on robots doing many tasks, and a failure of the field is it takes one graduate student 1 year to do one task on a robot, and we've got to change that. So I have proposed, and any of you can send me a donation, just of any size, to focus on the following problem. I want a robot to cook 1,000 different meals because I believe cooking involves at least 100 different generalizable subskills. So I think trying to do 1,000 different tasks is going to force us to do generalization much better. It will also remove the need for me to do any cooking in the future whatsoever. So there's a double bonus there. A triple bonus is cooking involves deformable objects, liquids, granular materials. So we have to confront situations where we don't have good models. So I think cooking is the way to go. So consider this a Kickstarter campaign to build a cooking robot. Send me your donations. Operators are standing by. Other questions? Yeah.
So it seems that most of the state-of-the-art demos are say from Boston Dynamics or even the RMS challenge. It turns out that very little learning is
Correct.
used. Well, we do see some impressive applications of learning, say the helicopter.
Which helicopter?
Well, I don't know, Drew and Peter and the helicopters. So what's the gap here? Or putting it another way, what would be a...
All right. Since you picked the helicopter example, I didn't pick it. Here goes. I have to find myself a web thing. I have to find myself YouTube. This is so exciting. I have to go to my channel. And let's see if I have it. Ooh, 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 ooh. So in 1991, before Drew was born, let me crank up is the volume? Why am I not getting, I never get any volume on these YouTube things. Okay, we're flying a helicopter indoors. This is like taking the casing off a lawnmower, spinning it up to full speed, and then dancing around it, waiting for it to chop our heads off. This is a lawnmower-sized helicopter flying indoors.
Do the inverted
Okay.
acrobatic.
Wait.
But this is impressive.
Is it? Is it?
Well, what's funny is just...
Are you impressed?
Are you running the...
Okay, you want to know what we discovered?
Yeah.
Traditional linear control techniques work just fine on helicopters. You want to know what we did? We said, oh, this is too easy, we'll go off and do other things.
But, I mean, you guys are standing upright, right? You're in a linear region.
Okay, we're flying indoors, a foot off the ground. You know what the ground effect is like? Do you know what the flow is like of the air in this room? Do you know what the people are like hiding behind every piece of furniture? At any moment, the blades will fly off, terrible things happen. My point with a helicopter is very simple. Things can look very impressive, but they just aren't that hard. What's hard about flying the helicopter is a human pilot has to do the kinematic transformations when the thing's upside down. And humans have a lot of trouble with kinematic transformations. But, you know, basically all these people did linear quadratic regulators or DDP, did local linear models. It essentially was no different than the swing up that I demonstrated. It's just not that hard. It looks good, but it's not that hard.
No contact, which makes it easier than anything we do with a robot.
Right. In many ways, like walking, it boils down to a state estimation problem. If you can do good state estimation, flying a helicopter is easy. And you want to know what the joke is? I got 3 minutes. You want to know what the hilarious joke is? It is, you know, flying these one rotor helicopters is hard. But when the quad rotors came along, flying a quad rotor is super trivial. It trivialized everything. And we actually built a quad rotor, and then we said, oh, this is really simple. We don't want to do this. So we bagged it and moved on.
But what is simple and what's complex? That's the question.
Okay, this is what the strategy thing is all about.
The visual perception is complex. For example,
Yes, visual perception is
Shaw has the same thing. He says, oh, for self-driving cars, control is so easy. You just go left or right.
correct.
Of course, perception is so
Correct.
In our robots, everything is very complicated. Of course, if you add vision, then it becomes very difficult. I mean, of course, these are blind. That's why it's easy.
Okay,
They see nothing.
remember-
Bumper on the trees, you throw your quadrant around.
Remember what I said. If you can do good state estimation,
This is if my
then
grandmother-
life is easy. The translation of those words from my language to your language is, if you can finally make computer vision work, everything is easy.
That makes sense.
That's what I said, right there.
That's beautiful. That's a beautiful, very acceptable conclusion.
Excellent, excellent. Oh. We let this thing get out of control. So, okay, I'll tell a sad story. I became a junior faculty member, and my first project was to take this massive, supremely capable direct drive arm and have it juggle one ball using visual feedback. You know, so we're watching the ball. And it learned to do this. Initially, it hit the ball goes way the hell over here. Hits the ball goes way over the hell. But fairly rapidly, it does it. Eventually, it's going to screw up. And we were so happy. Later, about a year later, we were thinking about it, and we realized that, I don't know why it stopped, the vertical control can be done without any vision at all, as long as you slow down when you're hitting the ball. Because if the ball has too much energy and comes down late, you'll hit it more slowly. If it has too little energy and comes down too soon, you'll hit it faster. That's enough to stabilize the vertical height. You don't have to see the ball at all. In order to stabilize horizontal, what you do is you have essentially a trampoline. Because if you go in the center, you get a cloth that does this. If you go on the side, the cloth is steeper, so it throws it back to the center. So what we did is I replaced that paddle with the beach things. You hit balls back and forth with the cloth stuff. I threw away the incredibly expensive vision computer I was using, and we just had the robot follow a fixed sinusoid, and it worked just fine.
Right, but it's harder. This beats the MacGyver thing that you want to do.
Yeah.
MacGyver would have used vision probably. It's easier to do it with.
No, it's much easier to do it blind. I swear to you, get rid of that vision crap. Okay, and let me tell you the rest of the story. There was a professor at Yale, Dan Kodacek, And there was a former professor here at CMU, when he was a graduate student with Dan Kotichek at Yale, he was so proud to build a strategy called a mirror strategy that mirrored the ball coming down, and it would hit the ball and it could juggle. So they did a version of this. And I pointed out to him that's entirely the wrong way to do it, because if the ball's accelerating downwards, the paddle's going to be accelerated upwards if you're mirroring the ball. And then he did 2 balls at once, okay? And he was so proud, and they sent me the video, and he came and visited our lab. And while he was there, we took this robot that had 1 paddle, and we bolted 2 other paddles to it. Now they're all moving with exactly the same motion. We took 3 balls, 1 on each paddle, and it's sitting there paddling 3 balls. So we won the world's record for most balls juggled by a robot right there. It took 5 minutes. Okay, so there's some value of doing things the easy way. Okay, I'm over time. Thank you very much.